So let's update our chart. Okay, now you can clearly see what's keeping us up at night. And we're not the only ones that have come to the conclusion that a single UPS is not reliable enough. Lots of smart people have worked on solutions. There's no standard solution, but the common approach is to throw more redundancy at your design, usually by adding a second UPS. And often this is done by using a feature of the UPS that allows it to be paralleled with other UPSs. The problem with this approach is that it doesn't really change your position on our graph. You still have a big, complicated component keeping you awake at night. You've just added one more, and it's connected to the other UPS. More interconnected, complicated components is seldom a solution that yields increased availability. The approach we've taken for a long time is to power our servers with two independent power lineups. By independent, I mean each lineup has its own switchgear, its own generator, its own UPS, even its own distribution wires. And by keeping these lineups completely independent all the way down to the rack, we're able to provide very high availability and protect ourselves from issues with the UPS. And while we don't love our UPSs for the reasons I've mentioned earlier, this redundancy performs very well. In fact, our data centers running this design achieve availability of almost 7 nines. But if you want to be an amazing operator, you need to constantly push to improve. And as you can see in this peculiar quote, you can't just ruminate about how to make things better, you need to act. So how do we improve our power design? Well, we need to address the big blast radius complicated component, the UPS. And let me show you how we did that. Rather than using a big third-party UPS, we now use small battery packs and custom power supplies that we integrate into every rack. You can think about this as a micro UPS, but it's far less complicated. And because we designed it ourselves, we know everything about it, and we control all the pieces of the software. And as we discussed earlier, this allows us to eliminate complexity from features we don't need, and we can iterate at Amazon speed to improve the design. Now, the batteries can also be removed and replaced in seconds rather than hours, and you can do this without turning off the system. So this allows us to drastically reduce the risk of maintenance we need to do to the battery shelves. The end result, we eliminated a big blast radius, high complexity, failure-prone UPS, and we replaced it with a small blast radius, lower complexity component. Now, this is exactly the sort of design that lets me sleep like a baby. And indeed, this new design is giving us even better availability than what I showed earlier. And better availability is not the only improvement we get from this new design. I'm going to come back to this later when we look at sustainability. But for now, I want to stay on infrastructure. Like the example I showed you here today, we are continually investing in improving the availability of our infrastructure. But we are also aware that no matter how good our infrastructure design and operations, some level of failure is inevitable. Physical events like fires, floods, hurricanes, tornadoes are tangible proof that you cannot achieve extremely high reliability from any single server or even a single data center. After we launched Amazon EC2, availability zones were one of the very first features that we added. At the time, the idea of an availability zone was a brand new concept to most users. But this idea was not new to Amazon, because this is the way we had been running our infrastructure for a long time. About 5 years before we launched AWS, we made a decision to expand the Amazon.com infrastructure beyond the single data centers that we were using in Seattle. Several operational near misses made it clear that we needed an infrastructure strategy that allowed us to run our critical systems out of several data centers. One of the leading ideas at the time was to move our system to 2 data centers, one on the West Coast and one on the East Coast. This is the availability model used by most of the world at that time, and it's still common today. And while this idea seems compelling at a high level, it loses its charm quickly when we get into the details. Amazon is a highly stateful, real-time application that needs to do things like keep inventory information up to date and consistent while all the users are accessing the website. And when you're trying to keep data that changes this rapidly synchronized with either strong or eventual consistency, latency matters. With a synchronous strategy, the latency between your replicas will directly impact your maximum transaction rate. And with an asynchronous strategy, the higher the latency, the more out of date your replicas will be. And for Amazon, where millions of customers are accessing real-time inventory information and making real-time changes to that information, neither a low transaction rate nor out-of-date information is acceptable. And this problem isn't unique to Amazon. All modern high-scale applications need to support high transaction rates and seek to provide up-to-date information to their users. So the obvious solution is to run from multiple data centers located closer together. But how close? Like all good engineering challenges, we have a trade-off. The further apart you put two data centers, the less likely they'll be impacted by a single event. On one extreme, if you put two data centers across the street from one another, it's pretty easy to think about things that might impact both data centers. Common things like utility failures, to less common things like fires and floods, to unlikely but really scary things like tornadoes. But as you get further apart, the probability of these sorts of natural disasters goes down quickly. And once you get to miles of separation, even natural disasters like hurricanes and earthquakes are unlikely to have a significant impact on both data centers. Now you can keep going, but after a while, you need to start imagining some absurdly low probability disasters, things that haven't happened in any of our lifetimes, to imagine simultaneous impact. And of course, on the other side, adding distance adds latency. The speed of light's a pesky little thing, and no amount of innovation speeds it up. Here I've added some estimates for how much latency would be observed as we move our data centers farther apart. The conclusion we came to is that for high availability applications, there's a Goldilocks zone for your infrastructure. When you look at the risk, the further away the better, but after a handful of miles, there's diminishing returns. This isn't an exact range. Too close varies a little based on geographic region. Things like seismic activity, 100-year floodplain,